Okay, so we're gonna
Okay.
do stoichiometry. So
Okay.
how I want us to do it, it's similar to how we do our lessons every time. We're gonna
Okay.
start with the basics, and then as the lessons goes, we're probably gonna build it up.
Okay.
So hopefully, I guess if we don't finish today, I would want us to continue tomorrow for questions so that we
Okay.
can do like exam questions after the basics. But today, I
Okay.
want us to cover more or less the basics, right?
Okay.
Right. So with stoichiometry, I want us to get to, we're gonna do the definition,
Mm-hmm.
right? Like how
Yeah.
we always normally do our lessons. We define what it is so that we understand, right? And then from
Mm.
there, we're gonna do the stoichiometric calculations, right?
Mm. Okay.
So this is where we will spend more time here. But from here, firstly, before we can actually do proper calculations, we're gonna start with the basics of more calculations.
Mm.
So from here, for your exam question, they probably won't just ask you more calculation. However, when you are doing your calculations, you would have to pass through this, right? And
Mm.
then again, you would have your mass to mole or mole to mass calculations, or we can just call them
Mm.
mass calculations, right?
Yes.
So you see, I've already been introducing terms now. There are moles, there are mass, and then you'll get to hear more words when we're defining like particles, of which I suspect you already know, but it's good to go through those, right?
Mm.
So after
Yes, it
that,
is.
we're gonna go through limiting reactions, like
Reagents.
limiting agents and stuff,
Yeah.
right? So by that time, when we get there, you would have known most of your basics, and then you are just applying,
Okay. All right.
right?
Yes.
Okay, so we are on the same page.
Mm. Okay. It's quite a few definitions.
Yeah. So other definitions we will define them as we go, but it's not a train smash, right?
Okay.
So we're gonna do the basic one. So we said limiting agent, and then we're also gonna do the percentage yield relationship as well. I think it's still
Yeah.
under this.
It is.
So so we're gonna do it like that, right? So we're gonna go
Mm.
as much as we can today and
Mm.
put questions, and then maybe tomorrow we do these two, and then we put questions. We'll see how it goes, right? All right. So we start with the definition. So how do you define? What do you understand about stoichiometry?
It's calculations that determine number of moles and all the like number aspects towards a chemical reaction. Mm.
Okay, so that is more or less what stoichiometry is. But just to summarize what you just said as well, we can just
Mm.
say, you mentioned, okay, let's put what you said first. You mentioned reactants,
Mm.
right?
Yeah.
And you also mentioned products, did you?
Mm.
And then
I
you,
mentioned a chemical reaction.
okay, so, okay, I'll put products just the, and then there is a chemical reaction,
Mm.
right?
Yes.
And you mentioned something about calculation,
Mm.
right?
Yes.
Okay. So what did you say all together?
It's numbers relating to a chemical reaction. Like how much of reactant is needed to produce that much of a product. Like how many moles of this will react with how many moles of that. I don't know how to put it into words.
Yeah, so you will have to put it into words just in case they put it out there. But however, like you
Mm.
are saying, that it's a matter of how many reactants that are needed to actually give you products in a chemical reaction, right? So it's like x and y. For example, if ever in maths you are saying 2x plus 4 is equal to y, what do we
Mm.
call that in maths? What do we
An
call it?
equation.
Like it's an equation, but what is happening between x and y?
There's a relationship.
Exactly. That's the word I want, right?
Mm.
That's a word that is missing here. It's a relationship,
Mm.
right?
Okay.
So, but what type of a relationship is it between these reactants and products? You said it's how many reactants you need to actually get products. The word how many, it talks about measurements because you want to know how
Mm.
many, therefore it's a measurement of something. And then in one word we say that is quantitative or
Mm.
quantitatively, but it's
Yeah.
quantitative measurements, you see. So that's another word that you will find when you are defining stoichiometry,
Stoichiometry.
right? I'm
Yeah.
gonna just put these words here, then the combination will come out, right? So we
Mm.
are talking about a quantitative relationship, right,
Mm.
between the amounts of reactants that are
Yeah.
used and amounts of products that are formed by chemical
Mm.
reaction. Finish. We used everything that is here.
And amount of.
So we are saying it's a quantitative
Mm.
relationship
Yeah.
that is done between,
Amount of reactants
yes, the
used and
amount
amount of products formed by a chemical
of,
reaction.
yes, of reactants used and
Amount of products
amounts
formed.
of products formed by a chemical reaction. So there has to be a chemical reaction for this, right?
Yes.
So chemical reaction. So I'm giving you now, when you are answering in an exam question, let's say you are defining stoichiometry,
Mm.
the person marking is gonna want to see chemical reaction. You mention the amount of product, you mention the reactant, and you mention the quantitative relationship, because there has to be a measured relationship between what is going on, right? So this
Mm.
already summarizes what we're doing, that we're going to be doing chemical reactions, and we will just be calculating how much reactants we need to actually form whatever we are forming, right? It's like how
Mm.
many, what is a measure you have in, let's say you are baking or you are cooking. Whatever you're cooking, you already have your ingredients. You know you're gonna need salt, you're gonna need sugar, you're gonna need spices, right?
Yeah.
But this is the word that there's a big but. How much you gonna need to actually
Mm.
produce what you want? The word how much changes in everything, because you can put as much sugar you want, but let's say you don't want something salty. There's a difference between something salty and something not so salty, right? It all
Mm.
depends on how much salt you put in to actually get the product that you want, right?
I see.
So
Yeah.
even here, it's the same thing. You can, let's say you combine two reactants or elements that you are doing, but
Mm.
it all lies in how much you're gonna put to get this much, right? And
Mm.
then that
Yeah.
where the moles and the messes and everything comes into play, because that's gonna help us in determining the quantitative part of the
Mm.
reaction, right?
Yeah. Yes.
So now we are done. We understand stoichiometry, right?
Mm. Yes.
Same thing here with stoichiometry. Remember last time we spoke about conservation of what was it? Was it electrostatics in electrostatic? But we spoke up.
Conservation of charge.
Yes, we spoke about conservation of charge in electrostatic, right? And then I said to you, it's still the same thing. In an isolated system, whenever we're talking about conservation of something, it means it still needs to remain the same. So in here, you're gonna hear some things about conservation of mass. Still the same English words. It means mass is conserved. It has to stay the same in that reaction, right?
Mm.
So we are introducing another word here, conservation of
Of,
mass, right?
yeah.
So that one is we know that the law of conservation, regardless of what it is, it means that
Mass
like
cannot be created or
in this
destroyed.
case, yeah, that's why I'm saying when you hear conservation, doesn't matter momentum, mass, energy, charge, always have that you cannot create or destroy it. It has to stay the same. In this case, it will be in a chemical reaction because we're talking about chemical reactions, right?
Mm.
Yeah. So in this case now, the amount of matter present at the end of the reaction is gonna be the same as
The amount of matter in the end of the reaction.
no, I'm saying in the end of the reaction is gonna be the same as
It's the same as the beginning. Sorry.
exactly, yes. So it's gonna be the same as the beginning. So that's what we mean here.
Mm.
So why am I talking about this? Where are we going with this?
From the conservation of mass,
Yes, so now we spoke about conservation
the
of
mole
mass, right?
concept.
And then I said to you, at the beginning of the reaction, the
Mm.
mass, the amount of matter that is present or the amount of mass that is present should be the same or is going to be the same of the amount of matter at the end. So why am I telling you that? It's because when you are doing with chemical reaction, you have reactants, you have products. Therefore, that means that you have to make sure that the mass of reactants is equal to the mass of
Products.
the products. So that's where we're going with this.
Repeat one more time.
So
Where
we're
we are going
talking
with it?
about conservation of mass, right? And we spoke
Yeah.
about the fact that the amount of mass present in the beginning of a reaction is going to be the same as the amount of mass at the end, right? So that means mass is conserved. And therefore, that means that the mass of reactants,
Mm. Is the same as the mass of the product.
the mass of the reactant is the same as
The mass of the product.
the mass of the product, right?
Yes. Yes.
So if ever I have the total mass of my reactants of whatever I used to get the product, it's 24 grams, right? But this is a combination of all the reactants. This
Mm.
should be the same as the mass of the product.
Mm.
This should also be 24 grams at the end. So
Mm.
I start with this, I do whatever I'm doing. At the end, I have a product. Conservation of mass says this and that should be equal,
Yes. But
right?
are they?
No, with this, that's why when we are doing stoichiometry, you're gonna have to make sure that it is balanced like that.
Okay.
So
Okay.
mass is conserved, so it is gonna be like that. And then when you are calculating and it is not like that, that means you have done something wrong because mass has to be conserved.
Okay.
The total mass should be unchanged. Ne?
Mm.
So if ever you are doing calculations and then you are balancing out, then you're like, this is not balancing. The
Mm.
mass is not conserved.
I see. Okay. Okay. But then what? If mass is not conserved, then what?
Then you are supposed to balance out your chemical reaction. And then if ever mass
Also,
is not
when
conserved,
okay,
there is the
it's not
external,
balanced.
yes. That means now there are external factors in your reaction. That means that there are
Okay.
catalysts or whatever that you're using now to produce. It's no longer an isolated system, just you and just the reactants only. That means there's an external force. If ever now you end up with more mass than you had, you see.
Mm. Yeah. Okay.
So this is what happens when you are talking about a balanced equation, right? This
Okay.
happens when you are talking about a balanced equation, right?
Mm.
Okay, so we're
Okay.
gonna move on. I just want to see on my notes here. Okay, so I'm gonna give the other terms are gonna come as we do examples, right? So I'm gonna write an example here, and then we're gonna interpret it together,
Okay.
right? So I'll start with this one. So you have hydrogen plus nitrogen. I'm sure you've seen this so many times to give you ammonia, right? So in this case here, you are starting. You have your
Mm.
ingredients, which are your reactants in this case. Just gonna put the
Yeah.
word ingredient so that you understand it in practical terms and in chemistry terms, right? So you have your
Mm.
reactants as hydrogen and nitrogen to give you
Mm.
ammonia,
Ammonia.
right? So
Mm.
now we're talking about elements, or let's say particles to say. However, for you to start, you have to ask
Mm.
yourself one question: is the equation balanced?
I don't think so. No, it's not.
So, what do you look at when you are asking this question? What do you look at?
Well, the amount of particles on either side, the mass.
You see, now what you are talking about, you mentioned amount,
Mm.
right?
Yeah.
So, the amount of substance that you are using
Mm.
has to be the
Mm.
same before and after, right? So,
Mm.
we check
Yeah.
the amount of hydrogen. We have
Yeah.
6 hydrogens on this side,
Mm.
right? 6.
Yes.
And then on this side, we have 2. So we have to
Mm.
balance this out. And 6 divided by 2 is 3. Just
3.
pure maths. If you can do it either way, if ever you have 6 this side, you already have 2 here. For you to get 6, you multiply by 3. Just
Mm.
pure maths. And then you
Mm.
have 2 nitrogens here on this side, and here you have 2. So that means that balances out, right?
Mm.
So now
Yeah.
our equation is
Balanced.
balanced,
Mm.
right? And then we can
Yes.
start talking now, right?
Mm.
We can start talking and say, what is this now? You see, we have coefficients now. There are coefficients here. There's a 1 here and there's a 2 here. And then we were balancing out. What were we doing? What are those coefficients called that are used to connect all substances in the reaction? Because we were trying to connect reactants. Remember, we said this is a relationship stoichiometry. So we were trying
Mm.
to connect the reactants to the products, and we introduced these coefficients. What are those? What can you say is happening here? What are these?
It can't. It's the number of molecules, I think.
Yes, so this is moles. We say
Okay.
moles. I want to
Moles.
introduce the terms. This is moles. This is the
Okay.
number of molecules, right? And then these coefficients are telling us the relationship or the ratio between reactants and products, right? So here we have a ratio of 3:1:2. That means you have to have 3 of hydrogens, nitrogens to get 2 of ammonia, right? This is a
Yeah.
ratio that is happening in this reaction.
Mm.
Also, we say it's molecules, right?
Yeah.
So now what does this ratio mean? It means regardless of how much you have to actually give you a certain amount of ammonia, but you will always stay in a ratio of 3:1:2. Does it make sense?
Mm.
So let's say the total amount that you end up using, it's a certain number to say, but when you are doing a ratio, it has to stay 3:1, right? So
Mm.
let's say here,
Okay.
if ever I have 6 then that means here I will need to have
Repeat that
2.
again. About it has to stay 3:1.
So what, let's say now the total amount of hydrogens you use here, it's like you have 6, and then here you have 2, and then here you have 4. This ratio is still the same. It's still 3:1:2, right? So what
Okay.
I'm saying is the molecules or the coefficients might not be 3:1:2. However, the ratio is gonna stay 3:1:2 on this reaction to balance it out.
Okay.
Does it make
Right.
sense?
Yes. So even if it reacts in 6 hydrogen and 2 nitrogens, it's still gonna give you the same 4 molecules.
Yes, it's gonna give
Okay.
you the 3:1:2.
Okay.
All right. So we the mass of an element you will be given, right? Or if ever you are not given, you're gonna have to calculate it. Mass is mass, it's in grams, right?
Yes.
All right. So I want to have another one now that we're gonna interpret and take out molecules and then take out what do you call a mass. Okay. So I'll write this down for you. So we have 4. I'll just write it down from my notes. And then, so we have ion, 4 ions, we have 3 oxygens, we have, sorry, we have 2 iron oxides. This is a solid, right? Okay, so S, you know what S means?
Solid.
And then this is gas, this is solid. Just putting it out there so that you know how to interpret your equations, right? So we
Yes.
have to now interpret this equation in terms of representative particles. That is, what is it that you see, like we were doing on the previous, what you call previous equation, right? So how are you gonna say it? With this one, you're gonna say,
4:3:2.
okay, so that is your ratio. This is 4:3 is to
Is to 2. 2.
is to 2. Right? That means you're
Yes.
gonna you have 4 atoms of
Iron.
ion and 3 molecules of oxygen of O2 and 2 formula units, they say, for this product here, which is a solid. Or you can still say your molecules here 4:3:2, as long as you get that ratio, right? So this
Yeah.
ratio, we said 4 moles.
To 3 moles.
Just put it there. So that is your ratio,
Mm.
right? So now this is this moles. So now we need mass, right?
Yes.
Okay, so like we did mention this, I'm just reading my notes, that you need to remember that the coefficients in an equation represents not only numbers of individual particles, right? It is numbers of individual particles. It's this number for this particle and that number for that particle. However, we also said that it also number of moles of the particles. Therefore, you can also say that 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron oxide. That's what we said, right? Should I repeat that? Oh, it's you.
4 moles of oxygen reacts 3 moles of 4 moles of iron reacts with 3 moles of oxygen to form 2 moles of Fe2O3 iron oxide.
Yes, so that's what it means, that it does not only represent individual particles, but the relationships that says you need 4 of this and 3 of this to actually get 2 of this, right?
Mm.
So
Yes.
always, when you are given an equation, think, even if you're not going to write it down, let your mind think it that way. When you see the
Mm.
numbers, relate them to what it means.
Mm.
Okay, so when you are seeing a chemical reaction, right? So that chemical
Mm.
reaction, you can't see a chemical reaction and immediately you already know the masses of the reactants and the products. Does it make sense? So if I see this equation, do you already know what are the masses and the products of that? Can you tell?
One more time.
So what I'm saying is, on a chemical reaction, can you tell what is a mass of iron? Or what is a mass of the iron oxide?
No.
That exactly.
No.
So what I'm trying to say is, on a chemical, the chemical equation itself does not directly from it tell you anything about the masses of the reactants and the products, right? So that means
Mm.
you will have to calculate those.
Mm.
You can know the mass of individual element or particle, right?
Yeah.
But what about 4 moles of that?
What? Sorry. One more time. You
So
have
if
four
ever
moles of that.
you, yeah,
Yeah.
you know the mass of something, right? But you
Yeah.
don't know 4 moles of that. So what I'm saying is
Mm.
you will have to calculate it.
Yeah.
Right. So that's where we are going. The masses of reactants or masses of products you will have to calculate, right?
Mm.
So in this case, we have an element of our ion, right?
Mm. Yeah.
Okay, our thing is running out. We will have to do this until we're done, like the 40 minutes all the time. Then you
Okay.
have to rejoin and stuff.
All right.
We have iron. So you need to know what is the mass of iron. I will tell you for these examples, but in your case, you will also be given or have a sheet with them, right? So in this
Mm.
case, I've already put it down that the mass of this is 55.85 grams, right?
Mm. Yes.
However, in this equation now, you know that you need 4 moles of iron, right?
Iron.
But what we have is, we have 55.85 grams of iron.
Mm. Yeah.
This one is per mole because this is one. This is one Fe, right?
Mm.
Did you get it? This is for 1 mole.
Yeah.
Do you get what I'm saying? So I
Yes.
need for 4. It's just, I'm just doing all this relationship, but it's merely 4 times what you have because it's like the coefficient of it. However, I'm just showing you the relationship here. This 55.85 grams is per mole, right?
Mm.
But if
So
you
you
have
multiply
4
by
moles,
four to
yes,
get it.
so that this and that cancels out. And then at the end, you have 4 times 55.85, which is,
Oh, let me put that on the calculator.
think it-
Uh, 223.4.
sorry, does it make sense?
Mm. It
Right?
does.
So now we have the mass of this. We know that the mass here is 223
Yes.
grams, right?
Mm. Yes.
This is plus and then plus. Okay, so we go to the other one. We go to oxygen,
Mm.
right?
Yeah.
So we know that oxygen 32 grams is 32 grams oxygen, but that one is for 1 mole of oxygen,
Mm.
right? That is a mass
Yeah.
of 1 mole of oxygen. Now we need for 3 moles of oxygen, right? So that
Mm.
means that and that will cancel out. We say 3 times 32, that should be
96.
32926. So
Yeah.
96 grams of oxygen,
Good.
right? So we
Yeah.
put it down there, 96 of oxygen.
Mm.
So now this is plus. So we want the total of this.
Mm.
So just add that on your calculator. So 223.
223 plus 0.4 plus 96.
Yeah.
319.4.
This is 319.4 grams. We
Yeah.
don't know. Remember, we said in a balanced equation like that, conservation of mass. So, what are we
Mm.
expecting? We are expecting this to be equal to, right?
Mm.
So, we have to check it.
Okay.
It goes back to where you're going. What happens if it's not? But you know it should be. So, you're
Balancing an
already
equation.
expecting. Yes.
Yeah.
So now we are going to the iron oxide. The mass of the product is calculated as, so I'm giving you now that we have 159.7 grams of one iron oxide. Ne?
Mm.
So this
Yeah.
is for 1 mole, right?
Mm.
But we
Yes.
have 2 moles of
Moles.
this. So that and that, the moles cancel out, and then we have 2 times 159, which is
Should be, yeah, 319.4.
319.4 grams.
Mm.
Okay, so we go back and put it here.
Mm.
And we can see that this and this is
The same
equal.
thing.
Yes.
Yes.
So conservation of mass.
Is true.
Yeah, so mass is conserved. Like as predicted by the law of conservation, the total mass of the reactants equal to the mass of the products. Right?
Mm.